Okay, so it seems that we are now live streamed. So
good. Oh, by the way,
I think we can still wait
yeah,
a minute or two because I see people keep coming.
Yeah, sure. And do you make a backup copy on your computer? Or?
I can try.
Good.
Yeah, it seems to be working, I hope.
Just in case. Yeah.
I said I agree to be recorded.
Well, it's on the record now, so.
Yeah. Yes, and by the way, who chairs? As you wish.
Well, you can chair, Sebastian, if it's okay with you.
Sure.
Okay, thanks.
Keep an eye on the population in the room. About its cardinality, I mean. Okay. Seems to have stabilized a bit. Maybe we can start, I guess. Because if we get too much delayed, then
yeah,
not cool. Good. So hello, everyone. So for this last session of year 2021, we'll have a couple of talks about random planar maps and scaling limits and this kind of objects. And so for this first talk, we have the pleasure of having Jean-François Le Gall from Université Paris-Saclay, who will give us a talk entitled Geodesics in Random Geometry. So please, we are listening to you.
Thank you, Sebastian and Bastien. It's a pleasure to be giving a lecture in this seminar. Okay, so what I want to do, I see problems. It's very strange, sorry. Oh, okay, now it's good. So I want to discuss a specific model of random geometry, which maybe I should call Brownian geometry, because it's very closely related in some sense to Brownian motion. And in this first slide, I will first try to explain the reason why introducing this random geometry. So the idea is to replace two-dimensional sphere S2 by a discretization, which is simply a graph drawn on the sphere, what I will call a planar map, for example, like on this picture here. And we want to choose such a planar map uniformly at random in a certain class. So for instance, it will be the class of all triangulations with a given number of triangles. And we look at this as a metric space, meaning that we consider a set of all vertices, which we equip with a graph distance. Okay? And then we let the size of the graph tend to infinity. So for a triangulation, we take more and more triangles if you want. And we want to pass to the limit to this on this random metric space after certain rescaling of the graph distance to get the limiting metric space, which is called the Brownian sphere or the Brownian map. Okay, so this is supposed here to be represented by this picture, which I will explain a little bit later. Okay. So what is interesting in this approach is that you really get a limiting object which does not depend on the class of planar maps you started from. Okay, and so there is a kind of universality property, meaning that you construct a continuous object, which is the same for all discrete approximations you can think of, in some sense. Okay. So the specific goal of the lecture is to discuss geodesics in this limiting Brownian sphere, in particular recent progress about what is called geodesic stars. Okay. So here is the outline of the lecture. So I will spend some time to recall the motivation, the construction of the Brownian sphere as a limit of rescaled discrete objects. And then I will give a direct construction of the Brownian sphere from another very familiar object in probability theory, which is the Brownian tree, also called the CRT. And then I will come to results about geodesics. And first I will discuss geodesics from a typical point of the Brownian sphere. And I will emphasize the confluence property of geodesics, which is quite important, especially for what follows. And in the last part of the lecture, I will describe some recent work about geodesics from exceptional points, and in particular, what I will call geodesic stars. Okay? So this is the general outline. So let me start with the presentation of the Brownian sphere based on the discrete approximations. So I first need to recall proper definition of a planar map. So a planar map is just a proper embedding of a finite connected graph into the two-dimensional sphere. And something which is very important, which I should emphasize immediately, is that we consider this object up to orientation preserving homomorphisms of the sphere. Okay, so we are only interested, if you want, in the shape of the graph, not in the details of the embedding. Okay. I should have said multi-graph rather than graph because we allow loops and multiple edges. In fact, there are also similar results when we do not allow this, but maybe you can consider that here. Okay, so here is, for instance, a planar map. So you should think of it as drawn on the sphere, in fact. And something you can do because your graph is embedded, you can define faces, which are the regions bounded by the edges. You can define the notion of a p-angulation when each face is incident to exactly p edges. And when p equals 3, of course, it's a familiar notion of a triangulation. P equals 4, you get a quadrangulation. So there is a technical point, which is that we deal with rooted planar map, meaning that we have distinguished an edge, which is also oriented. Okay? So this is a rooted triangulation with 20 faces. You can count the number of triangles. Do not forget the external one, because we are on the sphere. And here I've chosen the root edge to be this edge, for instance. So the initial point of the root edge is sometimes called the root vertex. Okay, so this is the definition of a planar map. I emphasize the fact that we look only at the shape of this object. So these two are the same planar map, but these two here are two different planar maps because you see, although it is the same graph structure, the embedding is different. Okay? You cannot deform this object to get this one continuously. Okay, so here is a simulation, I think, by Nicolas Curien of a large triangulation of the sphere. Here it's not drawn on the sphere, it's drawn in space by Mathematica, so that in some sense it is expanded in such a way that you see better the graph structure, or the edges have approximately all the same length. Okay. But you already see that you have quite a fractal structure for a very large triangulation of the sphere, and we will see that later also in the limiting model. Okay, so I said that we're going to look at planar maps as metric spaces. So if I have a planar map, so for instance here this is a quadrangulation, we can look at the vertex set, V of m, the graph distance on the vertex set, and so we get a finite metric space. So it's a very simple object in a sense, but what we're going to do, we are going to let the size of the map tend to infinity. So typically what we can do, we can fix an integer p, at least equal to 3, say, and we look at the set of all rooted p-angulations with n faces. For instance, all rooted triangulations with n triangles. Okay? In this way, we get a finite set because this corresponds to the identification I mentioned before. There is a finite number of possible shapes. And then we want to choose one uniformly at random in this space, M and P. And P is fixed, oh, sorry. And we want to let the number of faces tend to infinity. Okay? I want to pass to the limit, and so we pass to the limit in a sequence of metric spaces. So we view, in fact, the vertex set equals the graph distance as a random variable with values in the space capital K, the space of all compact metric spaces, modulo isometries. Okay? And to make sense of the convergence, we equip this set with a Gromov-Hausdorff distance. Okay? So, okay. Here is a brief reminder of the Gromov-Hausdorff distance. This is the definition of the classical Hausdorff distance between two compact subsets of a metric space. And now if we want to compare two compact metric spaces, say E1 and E2, what we do, we try to embed E1 and E2 isometrically in the same big space, capital E. So this is presented by the picture here. You have space E1 here on the left, E2 here, and try to have these isometric embeddings of psi1 and psi2. And we try to embed them in such a way that we minimize the Hausdorff metric between the embeddings. Okay, so we take the infimum over all these isometric embeddings of E1 and E2 of the Hausdorff distance of psi1 and E1 between psi1 and E1 and psi2 of E2. This gives us the Gromov-Hausdorff distance. And this distance has very nice properties. And if you look at all compact metric spaces modulo isometry, then this Gromov-Hausdorff distance is really a distance on the space capital K. And we get, in fact, a separable complete metric space, a Polish space. Okay? So we can make sense of a convergence of a sequence of compact metric spaces or of random compact metric spaces. Okay, so it makes sense to study the convergence in distribution of the vertex set of Mn, equipped with the graph distance. But what we are going to do, we are going to rescale the graph distance by here a polynomial factor, and the reason is easy to understand, simply because since we let the number of faces tend to infinity, if we do not rescale the distance, we cannot expect to get a compact limit. The distances are going to blow up. Okay? And so we rescale the distance by this factor n to the power minus a. And the correct value of a is chosen in such a way that the diameter of the vertex set for the graph distance is of order n to the power a. Okay? And it has been known for some time that the correct value of a is 1/4. Okay? So this problem was stated in the case of triangulations by Odedshram. Okay, so here is the result of convergence to the Brownian sphere, at least one result. And this is a reminder of the notation. You take Mn uniformly distributed over all p angulations with n faces, the vertex set, the graph distance. And here is the theorem. It says that for any p greater than or equal to 3, so if you rescale the graph distance by this factor n to the power minus 1/4, and there is an additional constant Cp, which is not so important here, then you get a convergence in distribution, the Gromov-Hausdorff sense, toward a limiting random compact metric space, this M infinity D, which does not depend on B. This is really the important property of universality. You get just only one limiting object independently of the discrete object you start from. And this limit is called the Brownian sphere or Brownian map. Okay? So in the case when p equals 3 or p is even, this was proved independently by myself and by Grégory Miermont a few years ago. And more recently, Dario Berri and Albank have treated the case of odd values of p greater than or equal to 5. And something I should mention is that there are extensions to many other classes of random planar maps. I've mentioned a few names. So roughly speaking, as long as you impose a certain bound on the degree of faces, you always get the same limit is the Brownian sphere. In fact, in the talk by Nicolas Curien, I think he will discuss cases where you allow very large faces and then you get a different limit. Okay, so what are the basic properties of the Brownian sphere? It's a geodesic space, meaning that any pair of points is connected by a geodesic, which may not be unique, but there is at least one. Okay, and Hausdorff dimension is equal to 4, almost surely. So there is a more recent result saying that there is a correct Hausdorff measure function, in fact, for the Brownian sphere, which is R4 times log 1/r. And one can prove, in fact, that the volume measure on the Brownian sphere, which I will introduce in a while, is equal to a constant times the Hausdorff measure with respect to this function h. But I will not discuss that today. And another theorem which I proved with Frédéric Paulin is the fact that the Brownian sphere is homeomorphic to the two-sphere. You should think of the two-sphere, but with a very wild metric, very irregular metric, so that the Hausdorff dimension is equal to 4. So I should briefly mention that there are important connections with the so-called Liouville quantum gravity. Okay, so in fact, Jason Miller and Scott Sheffield have developed a program showing that the Brownian sphere is intimately related to Liouville quantum gravity. And they derived a new construction of the Brownian sphere using the Gaussian free field and random growth process called the quantum Levenaar evolution. Okay? So this makes it, in fact, possible to equip the Brownian sphere with a conformal structure, which I will not discuss, of course, here. Okay? And more recently, this construction of Miller and Sheffield, which is quite complicated, has been simplified by a direct construction of the Liouville quantum gravity metric from the Gaussian Sheffield. So you no longer need this quantum Levenaar evolution. And, there has been several papers providing different steps toward this construction. I will mention here Ding, Dubeda, Falconet, and Dunlap. And there is also a paper by Green and Miller, which proved, in fact, the uniqueness of the metric. Okay, so let me come to the second part of the lecture. Now I will give you, I will forget about the discrete objects. It was mainly for motivation to explain why it is interesting to study this Brownian sphere, because it's such a universal object. Now I will explain to you a direct construction of the Brownian sphere from another very important probabilistic object, the continuum random tree, or CRT. Okay, okay, so again, the CRT can be constructed in different ways as a scaling limit of a discrete object, but here I will give the construction, I will focus on the construction of the CRT from the Brownian excursion. Okay, so to explain this, I can start again with something very simple in the discrete setting. If you have a plane tree like this one, okay, so it's a rooted ordered tree. Something you can do, you can imagine that you explore the tree from the left to the right. Okay, it's important that the tree is plane, meaning that there is an order on the, if you want, on the descendants of each vertex. Okay, so you can explore it like this from left to right. And the contour function is just a function that gives you the distance from the root, which is at the bottom here, in this evolution. Okay, so here you go up twice and you go down, then you go up twice and so on. So this corresponds to this step. You go up, you go down, you go up twice and so on. Okay, so this is a way of coding the tree, which is well known in combinatorics. It's called the big path of the tree. Okay, so we're going to do the same thing, but in a continuous setting, meaning that we're going to deal with continuous trees, and the continuous trees I'm going to consider are the so-called R trees. Here I will call them real trees, but it's really the same object. So what is an R tree or a real tree? It's a metric space. So for me, it will always be compact in this lecture. Okay, so it's compact metric space, such that if you pick any 2 points A and B in this space, well, there is a unique way of going from A to B in a continuous and injective way, like this. Unique path, if you want, continuous and injective from A to B, the red path here on my picture. And this path, the range of this path, if you want, is isometric to a line segment. Okay, and also we can decide that we root the tree if we distinguish a point rho, which is drawn here at the bottom of the tree. Okay, so you should think of an R tree or real tree as a connected union of line segments, as on this picture, which is a tree in the obvious sense. You have no cycle. Okay, so of course, okay, a real tree can be much more complicated. It can have infinitely many branching points, for instance, but still it can be well approximated by an object like this. Okay, so it's not, it's a good idea to think of a real tree as an object of this type here. Okay, and the coding by contour functions, which I just explained in the previous slide, also works to some point in the case of real trees. Okay, and it also yields an additional structure on the tree, which is a cyclic ordering. So let me explain that in the next lecture. So I start from a function g, which will be the analog, if you want, of the contour function I had before. So this is the red function here. It's defined on the interval 0, 1, takes non-negative values, it's continuous, it starts and ends at 0. I introduce this notation, mg of st is just the minimum of g between s and t. Okay? And then I can define a pseudo-metric on the interval 0, 1, dg of st, which is just g of s plus g of t minus twice the minimum of g between s and t. Okay? So this is only a pseudo-metric in the sense that it is symmetric, satisfies triangle inequality, but you can have distinct points at a distance 0. And in fact, this occurs exactly in this situation where you have t and t prime, where the value of the function g is the same at t and t prime, and between t and t prime, the value of g is larger. Okay, and then you identify t and t prime. Okay, so you take the quotient space of 0, 1 for this equivalence relation, you equip it with dg, which is now a metric on this quotient space, and you get a real tree, which is called the tree coded by g. So there is a volume measure, in fact, on this tree, which is just a push forward of Lebesgue measure under the canonical projection. Okay. So this canonical projection here will be denoted by PG. And it also yields a cyclic ordering of the tree, meaning that really the canonical projection corresponds, if you want, to continuous function that explores the tree in a certain order. And this is what I call the cyclic order. It's cyclic because you come back to the starting point. It's obvious that 1 is equivalent to 0 in this construction. Okay? So I can now give you the proper definition of the CRT. CRT is just the random real tree, which is coded by a Brownian excursion of length 1. Okay, so this is just a simulation of the Brownian excursion. You should imagine that we do the previous construction. We identify, in fact, 2 points which are at the same level, 2 points of the graph which are at the same level below the graph of the excursion. Okay, so here is a simulation due to Igor Korczemski of the CRT. And we need another ingredient to define the Brownian sphere. We need the notion of labels on the CRT, Brownian labels. So let me just define this for a deterministic tree. So you start from this object, TD, a real tree with a root rho, and you just look at Brownian motion indexed by this real tree. So this is a centered Gaussian process, which is 0 at the root, okay, and such that the variance of the increment of ZA minus ZB for any 2 points A and B in the tree is just the distance in the tree between A and B. It's just the same as the definition of Brownian motion indexed by the half line, if you want, but now it's indexed by a tree. Okay? So to make this perhaps a little bit more concrete, with each point A of the tree, you assign to this point a label ZA, and your label are going to evolve like Brownian motion when you move along the branches of the tree. Okay, so at the root the label is 0, but then imagine you move along this line segment of the tree here, the red segment, but the labels are going to evolve like linear Brownian motion. Okay, until point A. So the label ZA is distributed as the value at the time, which is the distance between the root and A of a standard Brownian motion. Okay. If you take another point B, you can perform the same construction, but of course, you are going to use the same Brownian motion for the evolution of labels, as long as you are on the common part of the ancestral lines of A and B. And then you use an independent Brownian motion. Okay, so I can now give you the definition of the Brownian sphere. So just a reminder of the notation. Okay, so now you start from the CRT. So in the previous slide, I had a deterministic tree, this TD, to define Brownian motion indexed by this one. But here I use now a random tree. Okay, this is the continuum random tree. And so this is, if you want, the first level of randomness. The tree is random. And given the tree, I also look at Brownian motion indexed by the tree. So it is a second level of randomness, if you want. Okay. And then I introduce this function, which is a bit similar to what we have done to define the tree coded by function, in fact. So for any 2 points A and B in the CRT, TE, we define this D0 of AB as the sum of the labels of A and B minus twice the minimal label between A and B. Okay, so what do I mean by between A and B? Here I say C belongs to the interval AB, and this is really vertices that you visit when you go from A to B using this cyclic exploration, which I described before, which you can interpret as a kind of clockwise exploration around the tree. Okay? So, of course, the vertices that you visit when you go from A to B in clockwise order are not the same if you interchange the roles of B and A's. So the interval AB is not the same as interval BA, of course. So here you take the maximum of these two minima. Okay. So this function is symmetric, but it does not satisfy the triangle inequality. So I define this capital D of AB to be the largest symmetric function of A and B, which is bounded above by D0 and satisfies the triangle inequality. You can get it as an infimum where you interpolate with finitely many points here between A and B, and you take the sum of the D0 of A minus 1, AI minus 1, AI. And then you play again the same game. You identify A and B. If D of AB is equal to 0, this can be shown, it's not trivial, to be equivalent to D0 of AB equals 0. And you define the Brownian sphere as a quotient space of the CRT for this equivalent relation, equipped with the distance induced by D. And again, you have a volume measure obtained by taking the push forward of the volume measure on the CRT. Okay. So just to summarize what we have done, we started from the CRT. So think of it as this object here with Brownian labels. So every point A of the CRT has a label ZA. We identify 2 points of the CRT. We glue them together if you want, if and only if they have the same label. And if you can go from A to B, for instance, here on my picture, just going around the tree on this red evolution here, and meeting only vertices with a greater label. Okay. And if you do this gluing procedure from the CRT, well, you do not identify too many pairs of points, in fact, but still you drastically change the topology because you start from a tree and you arrive at the Brownian sphere, which is homeomorphic to the sphere. Okay, so there is a very important property of distances in the Brownian sphere, which will play a key role later. So I need some notation. So pi is a canonical projection from the CRT onto the quotient space, onto the Brownian sphere. And of course, you can assign labels also to points of the Brownian sphere because, as I said before, points which are identified in the CRT have the same label. Okay. So if X is equal to pi of A, if X is the equivalent class, if you want, of a point A of the CRT, you can define the label of X to be the label of A. It does not depend on the choice of A. Okay. And the important fact is this one. You have to choose you consider a particular point of the CRT, which I denote by this A star, which is a unique point with minimal label. Okay. And you define X star to be its equivalence class in the Brownian sphere. Then distances from X star are simply given by labels, provided you subtract the minimal label on the CRT. Okay. So labels now exactly correspond to distances from X star. So this is very nice in some sense. In another sense, it's not so nice because you control only distances from a particular point X star. Okay, so you can say that, look, for me, it will. Okay, you can say that the Brownian sphere has 2 distinguished points, namely X star and the equivalence class of the root of the CRT. So for me, it's especially the first one, X star, which will play an important role. And one can say that in a sense, it's uniformly distributed over the Brownian sphere according to the volume measure. So it does not make so much sense at this point, but what this means is that if you look at the Brownian sphere as a pointed space, which is pointed at this X star, the law of this pointed space does not change if you replace X star by a point distributed according to the volume measure. So this means that the X star is really a typical point of the Brownian sphere. Okay, so this is really important for me because I'm going to discuss geodesics from this typical point, X star, and you should understand that the result will also hold if you replace X star by a point distributed according to the volume measure. So this was a reminder of the notation. So X star corresponds to the unique point of the Brownian sphere with minimal label. And as I told you before, distances now from X star to any other point X of the Brownian sphere are just given by the label of X here minus the minimal label. Here on this slide, I will denote it by the tilde X. Okay, to kind of, if you want to renormalize the label. Okay. So now consider a point X of the Brownian sphere. I can write it as the image under the canonical projection of a point A of the CRT. Now the CRT has also been constructed as a quotient space. So it was a quotient space on the interval 0, 1. So I pick one U in 0, 1 such that the equivalence class for the equivalence relation defining the CRT, the equivalence class of U is equal to A. Okay, this P was the canonical projection from 0, 1 onto the CRT. Okay? And the idea is now you can construct a simple geodesic from this X star, this particular point to X, the point I have chosen, by this formula. Okay. Well, what I do, you compose these two canonical projections, so one on the CRT and the one on the Brownian sphere. And you have here, well, you look in some sense in this cyclic exploration, which corresponds to the canonical projection P. You look at the last time before the time U here, where you have a label or renormalized label Z tilde equal to T for any T between 0 and Z tilde A. Okay. So informally, maybe I will, okay, not explain that too much in detail, but informally you have A, which is here. And what you do, you imagine that you explore the contour of the tree, but in reverse order from what I had before, backward if you want. Okay. In order, you look for points with smaller and smaller labels, starting from it. Okay. And this is supposed to be represented by this red curve, where you pick points with smaller and smaller label. Okay. So it corresponds to this parameter T here. And of course, at some point, you will arrive at the point with minimal label, which is this A star, which I have put here at the bottom of the tree. It's not the root of the tree, it's the point here with minimal label. Okay. So you construct in this way a red path arriving at A star. And what I say is that this is in fact a geodesic from A to A star. Okay. This is not at all difficult because it really comes from the fact that distances from X star are given by this explicit formula, are given by the labels. Okay. Okay, so here on my picture, of course, you get the impression that you have jumps, one sense that you jump from this point to this point on the tree. But in fact, in the Brownian sphere, it is not a jump because these 2 points are in fact glued together in the Brownian sphere. This is the idea. Okay. Remember this gluing procedure. Okay. Okay. Now, the difficult thing to prove is the fact which is here is that in this way, you get all simple geodesics from this particular point X star. And the thing I want to mention is that here you have some choices here because I wrote X as the equivalence class of a point A, so you can possibly, there are more than one point in this equivalence class, but in fact, this will not make a difference for the simple geodesics. Okay, you don't get more geodesics if you change A. On the other hand, here the choice of U is important. Okay, there are some points for which there are several possible values of U, and this corresponds to points which are not leaves of the CRT. Okay, so if A is not a leaf, you have several possible choices for U, and this will give you several geodesics between X star and X. Okay, so this is supposed to be represented here on the picture where A is not a leaf. Informally, you can start from each side of A here. Okay, either like the red curve or the blue curve. In the case when okay, maybe I do not explain that too much in detail. But here, of course, I give a precise result where I consider specifically the set of points of the CRT which are not leaves, this Sk of TE. So I remove the leaves of the CRT, and I define that this scale, which will be a subset of the Brownian sphere, as the image of Sk of TE under the canonical projection. In fact, one can prove, it's not difficult, that the restriction of the canonical projection pi to this Sk of TE is homomorphism, meaning that you do not identify in the CRT points which are leaves. Okay. Sorry, you do not identify points which are not leaves. Okay, so you do not identify points which are in this set Sk of TE. Okay, you can also verify quite easily that the Hausdorff dimension of this space scale is equal to 2, which means that it's a small subset, if you want, of the Brownian sphere, which has dimension 4. And the theorem now states that if you have a point X in the Brownian sphere, if it is not in scale, there is uniqueness of the geodesic. Okay. So this corresponds to what I was saying before. When you start from a point which is not a leaf of the CRT, you will have a unique, simple geodesic. Okay. On the other hand, if you start from a point of scale, which is so the corresponds to a leaf of the CRT, you get several distinct geodesics, and the number that you get is the multiplicity of the point in scale. The multiplicity is just the number of connected components if you remove X. Okay. Remember that you have something which is a tree or a homomorphic image of a tree. And it can be either 2 or 3 in this case. So this means that this at scale is the cut locus of the Brownian sphere relative to the typical point X star. Okay. Okay, so just an illustration, you should imagine in green here's the Brownian sphere, and you have this homeomorphic image of an R tree. It's non-compact because I have removed the leaves. Okay, but this cut locus scale is still dense in the Brownian sphere, and if you start from a point X, the geodesics from X to X star will move around in some sense this set scale, this tree scale, and you have the property which is again illustrated here that if you start from a point X, which is which belongs to scale, you may have, for instance, here 2 ways of leaving X, the blue one or the red one. Okay, so one word about the confluence property of geodesics. It's going to be important next, and so here is the fact. If you take 2 geodesics starting from points distinct from X star and going to X star, they have to merge before they hit X star. Okay, so you have 2 points X and Y. You take the red geodesic from X to X star, a green one from Y to X star. They have to merge, to coalesce before arriving at X star. But this is a slightly more precise version of the statement. If you want, it says that there is just one way of leaving X star along a geodesic. Okay, only one geodesic germ from X star. And this will also hold, as I said before, you replace X star by a typical point. In fact, X star is a typical point. Okay, okay, so why this confluence property? It's quite easy to understand from what I explained about simple geodesics before. And suppose that you pick 2 points A and B here. So I pick them on I view them as points of the CRT, but of course I'm going to look at the corresponding points in the Brownian sphere. I assume that A star is not in the interval from A to B, okay, meaning that you go from A to B following the contour, you do not meet A star, which is drawn here at the bottom of the tree. Okay, so and then the blue curve here and the red curve are supposed to represent the simple geodesics from B to X star and from A to A star. As I explained to you before, the simple blue geodesic, for instance, it's constructed. You start from B, you go backward on the tree, meeting points with smaller and smaller label. Okay, so at some point you will arrive at this point C, which is a point of minimal label between A and B in the interval AB. Okay, so you arrive here, and then you have no choice. If you want to find points with, again, smaller label, you have to jump over A in substance. You have to do something like this to arrive at a point C prime. Okay. In fact, these 2 points C and C prime will be glued together in the Brownian sphere. Okay. But then the point C prime here, it's very easy to see that by construction, it must also be on the red geodesic from A to A star. Okay. Because this red geodesic visits points with smaller and smaller label, and at some point it will also arrive at this point. Okay, so then the red and the blue geodesics, they have to merge. Okay, and so this is a confluence property. Okay, so let me come to the last part of the lecture. I think I still have 10 minutes. So I'm going to discuss now geodesics from exceptional points. Okay, so let me start with a case where you pick 2 points, any 2 points now, X and Y, which are typical points of the Brownian sphere, meaning, for instance, they are chosen according to the volume measure. Okay, then there is a unique geodesic from Y to X. Okay, and you may take, say, X equals X star, this is a typical point. And then, of course, the uniqueness of geodesics holds if Y is not in the cut locus. And we saw before, well, I did not mention it, but I said that the cut locus was a small subset of the Brownian sphere. In particular, it has 0 volume. Okay. So Y will not be in the cut locus, so you get uniqueness of the geodesic. Mm-hmm. Now, what happens if only X is typical? Then this is also what we saw before. You can have exceptional points. This was the point Y in the cut locus when I take X equal X star. There can be up to 3 geodesics from Y to X star, to X, okay. And now suppose that X and Y are both exceptional points. And then it was proved, I think, already in the paper by Angel, Kolesnik, and Mirmont, and also in the paper by Miller and Kian, that you can have up to 9 geodesics from Y to X, okay. So you can have much more in that case, okay. And in this recent paper of Jason Miller and Wei Qian, they even compute the Hausdorff dimension of the set of all pairs XY that you have exactly K geodesics from Y to X. Okay, okay. But I'm not going to concentrate on that, on these results. What I will do, I will discuss now geodesic stars. So what is a geodesic star? It's a point of the Brownian sphere such that it is the endpoint of n disjoint geodesics. Okay, so well, here's a picture. You have the point X and the black curves, the blue one, the red one, the orange one are supposed to be geodesics arriving at X. Okay, and you see that they are all disjoint, except of course that they meet at X. Okay. Now, because of the confluence property which I explained before, a typical point will not be a geodesic star. Okay, because geodesics cannot stay disjoint until they reach X. Okay. But you will have exceptional points, not hard to see, which are geodesic stars. Okay. Already, if you just pick an interior point of a geodesic, this point here, for instance, it is a geodesic star with 2 arms, obviously. Okay. And now the theorem I want to discuss. So it's this theorem I consider the set capital Sn of all geodesic stars with n arms. And then obtain that the Hausdorff dimension of this set is equal to 5 minus n for any choice of n equal 2, 3, 4. You could also consider geodesics with 1 arm, but then any point is a geodesic star with 1 arm, and the result is also true, of course. So this, in fact, Jason Miller and Wei Qian proved the upper bound for the dimension, and I completed their result by proving the lower bound. So there is still an interesting open problem. For n equals 5, one does not know that S5 is not empty, okay? Or is it not empty, okay? In fact, from the results by Miller and Qian, it is known that if S5 is not empty, its dimension is 0. But the question here is still open. Okay, so let me maybe make a short history of the subject. Well, I think the uniqueness of the geodesic between 2 typical points first appeared in this paper by Gregory Mirmont. Well, the results about geodesics from a typical point are essentially contained in that paper here. The notion of geodesic star is introduced by Gregory Mirmont in his paper proving the uniqueness of the Brownian sphere, where it played an important role. Results about what they call geodesic networks, meaning looking at all geodesics connecting 2 points, are first derived in this paper by Angel, Kolesnik, and Mirmont, and there is much more in this paper by Miller and Qian, which also proves the upper bound on the dimension of geodesic stars. So this is a paper where I proved the lower bound matching the upper bound for geodesic stars. And also I should mention that there are several related results in Liouville quantum gravity, which is a more general setting, because this Liouville quantum gravity metrics depend on a parameter gamma, and only a special value of gamma corresponds to the Brownian sphere. Okay, so in particular, this paper by Green and Miller deals with the confluence property, this one on geodesic network. In fact, this confluence property also played a major role in the proof of the uniqueness of Liouville quantum gravity metric, Liouville quantum gravity metric by Gwyn and Miller. Okay, so maybe in the last 5 minutes, maybe I will try to sketch the proof of the lower bound on the order of dimension. And for this, it's more convenient, in fact, not to deal with the standard Brownian sphere, but to deal with the so-called free Brownian spheres. It simply means that there is now a random volume, a random total volume. Okay, so the volume of the object is not equal to 1 in the case of the standard Brownian sphere, but it's randomized. Okay, and then you get nicer properties, especially spatial Markov properties for the Brownian sphere. Okay. And what you do, you define and approximate the notion of epsilon approximate geodesic star. Okay, so this is very similar to techniques that have been used to study exceptional times or exceptional points in different contexts. You just define, you say that a point X in the Brownian sphere is an epsilon approximate geodesic star. If you can find n geodesics arriving at X, which start from the boundary of the ball of radius 1, I should say the hull, I will explain that later, centered at X, which are disjoint up to the time when they arrive at distance epsilon from X. Okay, so they stay disjoint not until they reach X, but until they approach X at distance epsilon. Okay, and the two key estimates are these ones. The expected value of the volume of these epsilon approximate geodesic stars with n arms can be bounded below by a constant times epsilon to the power n minus 1. So this is first moment epsilon, first moment estimate, sorry. And you also need a second moment estimate, which is this one. In fact, it's a little bit more than a second moment estimate because you introduce this double integral where you have the indicator function, of course, of the set of epsilon approximate geodesic stars, but you also put a distance here between S and Y to this power here, to this negative power. Okay, and this is really needed when you want to get the lower bound of the order of dimension, because you can then use standard techniques. You look at the volume measure restricted to the epsilon approximate geodesic stars. You normalize this measure by epsilon to the power minus n minus 1, so the inverse of this quantity. You prove using the two estimates here that you can extract convergent subsequences that are going to be supported. The limiting measure is going to be supported on geodesic stars. And thanks to this estimate here, you also get an estimate on the limiting measure, which allows you to apply the classical Frostman lemma to get the lower bound on the dimension. Okay, so these are really the two key technical steps. So maybe I will explain the first estimate, and for this it's useful to introduce the notion of hulls. Okay, so what is a hull? You have to pick 2 points, X and Y on the Brownian sphere, and you assume that the distance between X and Y is greater than some R positive. And what is the hull of radius R centered at X relative to Y? Well, more conveniently defined by saying that its complement is the connected component of the complement of the ball of radius R centered at X that contains Y. So on a picture here, imagine that X is at the bottom here and that the vertical coordinate corresponds to distances from X. The ball of radius R is what you get below level R. But you have, of course, several, in fact, infinitely many, connected components of the complement of the ball. These are all these fingers here, this one, this one, this one above level R. So to get the hull, you add all these fingers except the one containing Y. Okay, so the hull is really this blue part here on the picture. Okay, you have just not added this part here. And what you can do, you can also make sense of the boundary size of the hull. So these points which are here on my picture. Okay. Okay, so what you do now, you consider this hull of, say, centered at always the same point X star relative to the other point X0 I introduced before. You assume that distance between X star and X0 is greater than R. And you have a nice description of the hulls which is very similar to the construction of the Brownian sphere introduced before, meaning that you can construct it not only using not the CRT, but a kind of poisson forest of R trees, again equipped with Brownian labels. And you should imagine that these trees are planted on a line segment 0U, where U is the size of the boundary of the hull. Okay, so one can make sense of this size. Okay, so you have all these trees going downwards like this one. And essentially, you can get the hull from this labeled forest by essentially the same construction as the Brownian sphere. Okay, in such a way that, okay, I forgot to say, your forest is conditioned on the fact that the minimal label is equal to -R. So labels start at 0 here. The points of the interval 0U here all have label 0, but you condition on the fact that there is one tree, let's say this one, so that the minimal label is on this tree and is equal to -R. Okay? And again, if you shift the label by +R, they will become non-negative, and they will correspond to distances from the point x star. Okay? So this is just repeat what I've just explained here. It's the same picture. And now you can get geodesics to x star by exactly the same manner as I did before. You want a geodesics that starts from the boundary of the hull, which is here. So you start from a point of this boundary and you follow, if you want, the contour of the forest now until you get points with smaller and smaller labels. Okay. And now it's not too hard to see that the event that x star is an approximate geodesic star with n arms. It occurs if and only if, in addition to the trees that carries x star, to this one, you have n-1 other trees in the forest which have labels, which have vertices with labels smaller than -R plus epsilon. Okay, so you need these other trees. Of course, they cannot have a label -R because they are conditioned to have a label greater than -R. But you require them to have a minimal label smaller than -R plus epsilon. Okay, because in that case, you see the blue geodesics here will coalesce with the red one only very late. Okay, only below level if you want -R plus epsilon. Okay, and it's not too hard to see that the probability of this event for probability of having just one tree with this property is of order epsilon. If you want n-1 tree, you have epsilon to the power n-1. Okay, so this leads to the first moment estimate. And I have no time to explain the 2-point estimate. This is my last slide. But basically, it relies on a kind of spatial Markov property on the Brownian sphere. So essentially, if you pick two typical points, it's x0 and x star, if you take hulls centered at these two typical points, then conditionally on their boundary sizes, okay, the blue hull and the green hull will be independent, and their distribution can be distributed in the same way I explained before when I had a single hull. Okay. Okay, so I think I'm already late. I should stop now. So thank you for your attention.
Well, thank you very much for your talk. So maybe we can start with a round of applause. You can unmute yourself.
Thank you.
And maybe a round of questions. So if you have questions, you can either raise your hand in the chat or just unmute yourself or write it in the chat.
Can I ask a question, please?
There is a question there. Yeah.
Sure.
Jean-François, thank you for your talk. I was wondering the construction you gave for the Brownian sphere using the Brownian motion on the CRT. Did you explain why this is the same object as the one you got from the limit? Because I missed that. Is that obvious or?
No. Thank you for your question. No, it's no. I did not do that.
Okay.
It would have been too long.
Yeah.
And I can explain the reason briefly. In fact, if you look at the discrete object, these planar maps I had before, and for instance, if you pick quadrangulation, there is a nice construction, a nice bijection between quadrangulations and trees with labels. Okay, but now discrete trees also equipped with labels. Okay, so there is a very nice correspondence. And what I do in this construction from the CRT, the continuous setting, is just an analog of the discrete bijection between discrete trees with labels and quadrangulations. So it's really not something that was invented directly in the continuous setting. It came from a discrete construction.
Right, and the labels in the finite object is Brownian labels as well, I suppose.
In the discrete setting, the labels they evolve like random walk indexed by the tree.
Okay.
And in the continuous setting, of course, you get Brownian motion.
So can it converge to some kind of Brownian motion when you do that? I see.
Yeah.
Okay, thank you.
Other questions?
Hi, can I ask a question?
Yeah, sure.
Okay, I noticed that you draw your geodesic almost always on the leaves of the tree, and you also mentioned that geodesic can, someone can kind of construct that using smaller and smaller labels.
Mm-hmm.
Is that obvious that the smaller labels always located on the leaves, or?
Yeah.
I'm not sure if.
That's an excellent question. In fact, I had too many things to mention, but you are completely right. Okay, where is my picture? No, it was before. It's here. Okay. In fact, one can prove that points that are visited by these simple geodesics, which are defined here, are only leaves of the CRT, except the starting point. Of course, the starting point does not have to be a leaf. But once you have left the starting point, you visit only leaves. Okay, so this has to be proved. It is not obvious. Okay, but it is true that when you look for points with smaller and smaller label, say the first point you meet, say with label T here, this one, it will always be a leaf. Okay, so this is on purpose that here my red curve or my blue curve, I made them visit only leaves because this is what you can prove. Okay, and otherwise, in fact, you would have several possible choices because when you have a point which is not a leaf, you can start from either side here. This is the red one or the blue one here. But when you are at a leaf, you have only one possible choice. Okay, so this fact that you visit only leaves, this is crucial for the properties of uniqueness of geodesics. Yeah. Mm-hmm. So thank you for your question. Mm-hmm.
Other questions? I may have one. When you define the Brownian map, you have this D0, this function with a max of 2 minima with the segment from A to B or B to A.
Yep.
And when we go from, my question is, if we have a vertex A that is here, when we go in cyclic order, it becomes 2 points, like there is one on one side, one on the other. So when we say we go from A to B, you understand the question?
I think I understand your question. You're completely right. It's also a very good question. You mean you can start from either side of A if it's not a leaf, but here you take the smallest possible interval. Okay, you mean you see, maybe I can show it on the picture here. Okay, maybe when you start from A and you want to go to B, for instance, you could say, well, I start by doing this, like this. You can start by moving. I don't know if you can see, but you see the red part here. You can already see it on this simple tree. The red part here is interval AB, and you have to start from the right side of A, of course. You don't start from the other side. Okay. The interval AB is the smallest you can get when you go from A to B, going around the tree, and in clockwise order. If you had the interval BA, you would start from B and you would visit all these points here, and so on. Or you would have to go around to arrive at A. You would have to visit the root, for instance, here. But I could have defined more precisely the interval. I didn't want to do it, but
this was very clear like this, but I wanted to be sure. But, yes, so yeah, the black segments we see at the tip of A and B, they appear neither in A to B nor in B to A. They are just thrown away.
Exactly.
Okay, thanks. That's what I understood, but I wanted to be sure. And I had another question. It's this free Brownian map with random volumes that enjoys the special Markov property. I mean, is this something new, or was it known a long time ago?
Yeah. No, it's not something new. It has been known a long time ago. It's very much related. If you know a little bit about excursion theory for linear Brownian motion, you know, when I construct the Brownian sphere, the standard Brownian sphere or Brownian map, I use the Brownian excursion with duration 1, sometimes called a normalized Brownian excursion. But there is another object, which is the Ito measure of excursion, which is in some sense more fundamental, for which the duration of the excursion is random. Okay, this is the measure that you get when you look at the Poisson process of Brownian excursions and Ito's theorem and so on. Okay, and the Ito measure, in some sense, is a much nicer object than the law of the normalized excursion, because, for instance, if you look at the excursion under the Ito measure, it's Markov. It's also Markov for the normalized excursion, but it's not time homogeneous Markov. Okay, it's time inhomogeneous Markov. Okay, so it's less nice in a sense. Okay, so you have nicer properties for the Ito measure of excursion. So if you do exactly the same construction of the Brownian sphere, but instead of starting from a normalized Brownian excursion, you start from a Brownian excursion distributed according to the Ito measure, you get this measure N0. Okay. This is just the difference, which is nicer because you see, essentially, the last slide I showed, this one, if you want to have some kind of spatial Markov property, some independence between the green part and the blue part, if the total volume is fixed equal to 1, you can never get independence because if you know the volume here, this will give you a bound on the volume here, okay? But if you deal with the free Brownian sphere, where the volume is random, you can get certainly an independence, okay?
Okay.
So you have nicer properties under this N0. Oh yeah, this is what I wrote here, in fact. It's only valid for the free Brownian sphere, not for the standard one.
Yeah, that's, yeah. Okay, thank you very much. I guess we will...
it's time for Nicola, I think.
Yeah, exactly. We'll stop questions here for the second talk. So second round of applause for thanking.
Thank you. Thank you. So I stop sharing my screen now, yeah?
Sure. And we can switch. And I don't know, Bastien,